In this lesson, we will define normal subgroups and show how they can be used to create new groups called quotient groups. So earlier, when we were looking at cosets, we saw that a left coset does not necessarily have to equal a right coset. So given a subgroup H of a group G, we looked at examples earlier that the left coset AH does not necessarily equal the right coset HA. So in particular, we showed that in S3, 1, 2, H does not equal H 1, 2 when H is the subgroup generated by the permutation 1, 3. So there are certain subgroups for which the left coset AH will always equal the right coset HA, and it was almost 200 years ago, around 1830, that a mathematician named Everest Galois first recognized the importance of subgroups that have this property, that the left coset AH will equal the right coset HA. So first, to recognize the importance of subgroups H, for which AH equals HA for all A in the group G. This leads to our following definition of a normal subgroup. So a subgroup H of a group G is called normal if and only if AH equals HA for all elements A and G. And in this case, if H is a normal subgroup of G, we denote this by H, and then it's kind of the symbol for a subgroup, but we close the less than symbol. So this is the notation for H is a normal subgroup of G. Now there are many equivalent definitions of a normal subgroup, and the next theorem will prove several other statements are equivalent to this statement of AH equal to HA for all A and G. And so any one of these following statements could have been used for the definition of a normal subgroup. So let's begin our theorem. So let H be a subgroup of G then the following are equivalent. So 1, H is a normal subgroup of G. Statement 2, this is just the definition of normal subgroup. So AH equals HA for all A and G. Three, A inverse is an element of H for all A and G and for all H in subgroup H. Statement 4, the coset A inverse, the conjugate of H by A, is contained in H, is a subset of H, for all A and G. And the fifth statement, the conjugate of H by A, so A inverse, actually equals the subgroup H for all A and G. So again, statement 1 is just the notation H as a normal subgroup of G. And so this statement, this theorem, shows that statements 2, 3, 4, and 5 are all equivalent, and therefore any one of these statements could have been our definition of what it means for H to be a normal subgroup of G. So for the proof of this theorem, we see that 1 is equivalent to 2 because this is just the definition of H being a normal subgroup. So this is just the definition of a normal subgroup. So to complete this proof, we're actually going to prove a chain of conditional statements. So now we will prove 2 implies 3, implies 4, which implies 5, and that implies 2. If we can prove this chain of conditional statements, then that will show that each statement proves the others. So now we continue by showing that statement 2 implies statement 3. So now suppose AH equals HA for all A and G. Then for all A and G and for all H in subgroup H, there exists an H prime in H such that AH equals H prime A. So the statement that the left coset AH equals the right coset HA does not mean that you can commute the element AH and that's equal to HA. What it means is that anytime you have an element AH, it is equivalent to some other element of H times A. So we just know that the two cosets as sets are equal. We don't know that the individual elements can commute. Well, since AH equals H prime A, we see that A inverse equals H prime, and that is an element of H. So for any element A and G, and for any element H in H, the conjugate A inverse is an element of H. So that proves statement 3. Now we show 3 implies 4. So we're going to assume that A inverse is an element of H for all elements A and G, and for all elements H and H, then clearly the conjugate of subgroup H by A inverse, which is just the set of all of these elements A inverse, such that H is in G, this whole set must be contained in H, since each of the individual elements is assumed to be in H. And that proves statement 4. Next, we'll show that 4 implies 5. So again, we're going to suppose that A inverse is a subset of H for all A and G. Then I can write the conjugate of H by A inverse as A inverse HA, which equals A inverse H A inverse inverse. This conjugate must also be contained in H. So we see that A inverse HA is a subset of H. Since A inverse HA is a subset of H, if I take the conjugate of both of these sets by A, we see that H, which can be written as A inverse HA inverse, this must be a subset of A inverse, but we already showed that this set was a subset of H. So the only way that H can be on both ends of this chain of subsets is if all these sets are equal. Thus A inverse equals H for all A and G. Now finally we need to finish our chain of statements by showing that 5 implies 2. Now to see this, let's note that AH equals HA if and only if A inverse, which I can think of as the left coset AH, then A inverse. If AH equals HA, then I can exchange AH with HA. But then this simplifies to HA inverse, which just equals H. So we see that AH equals HA if and only if AH A inverse equals H. So therefore, we've actually proved a stronger statement that 5 and 2 are equivalent statements. And this completes the proof of the theorem. So this theorem shows that statements 2, 3, 4, and 5 are all equivalent. So we see that statements 2, 3, 4, or 5 could have been used to define normal subgroups. So if we go back to the theorem, we see that if we want to show that H is a normal subgroup of G, we can prove any of these equivalent statements. So now we will give some examples of normal subgroups. First, note that every subgroup of an abelian group is normal. This is simply because you can commute the elements in an abelian group. So given a subgroup H and G, and A is any element of G, then AH, by definition, is the set of all elements AH such that H is in H. Since the group is abelian, this just equals the set of all elements HA such that H is in H, and that is the right coset HA. So any subgroup of an abelian group is normal. A similar example is the fact that the center of any group is a normal subgroup. So the center, denoted Z of G, of a group G, is normal. This just follows from the fact that any element in the center will commute with every element of G. So again, this follows from the fact that AH equals HA for any A and G, and H in the center of G. Now for a less trivial example, we prove a theorem about normal subgroups. Every subgroup of index 2 is a normal subgroup. So recall the index of a subgroup is the number of distinct left cosets, or equivalently the number of distinct right cosets of that subgroup in the group. So the basis of this proof is the fact that if there's only two distinct left cosets of a subgroup, then we'll see that every left coset will have to equal its corresponding right coset, and the proof really depends on the fact that there's only two cosets. So let H be a subgroup of G with index 2. So recall that means that there's only two left cosets of H and G. And then let's let X be an arbitrary element of G. There's two cases. Either X is an element of H or X is not an element of H. So we'll look at these two cases when X is in H or X is not an element of H. So first, if X is in H, then the left coset XH will just equal H, because when X is in H, the subgroup H just absorbs the X. But this is then also equal to the right coset HX. So we see that the left coset XH equals the right coset HX. Now we need to show the same thing when X is not an element of H. So now, suppose X is not an element of H. So since the index of H and G equals 2, there are exactly two distinct left cosets of H and G. H itself will be equal to one of the left cosets. Now, since X is not an element of H, and we know there's exactly two distinct left cosets of H and G, the left cosets of H must be H and XH. So these are the two left cosets of H, and these are disjoint sets. So every element in G is either in H or in XH. So because cosets are disjoint, everything in XH must be the elements of G that are not in H. So this must equal the set G minus H. That is everything in G that's not in H. Well, similarly, there are two distinct right cosets of H, and the two distinct right cosets of H are, they have to be H and HX for the same reasons. Since there's two distinct right cosets, everything in G is either in H or in HX. So again, by the same reasoning, we see that HX must equal everything in G that's not in H. So that's the set G minus H. Then we see that XH equals HX, because they both equal G minus H. So we've shown that whether X is in H or whether X is not in H, the left and right cosets are the same for any X and G. So since XH equals HX for all X and G, this shows that H is a normal subgroup of G. So again, this theorem states every subgroup of index 2 must be a normal subgroup of that group. So if you have a subgroup that's half as big as the group itself, then that must be a normal subgroup. So here's an example that illustrates this previous theorem. Consider the dihedral group D2n. There are 2n elements. There's n rotations and n reflections. So if we look at the subgroup generated by R, this must be a normal subgroup of D2n. This is because of the previous theorem, the index of this subgroup generated by R is equal to, since these are finite groups, this is the order of D2n divided by the order of the subgroup generated by R. Well, there are 2n symmetries in D2n, and there are a total of n reflections. So we see that the index of this subgroup generated by R is 2, and therefore this must be a normal subgroup of D2n. Now for another theorem about normal groups, if you have a subgroup H, and this subgroup H is the unique subgroup of G, of some particular order n, then H is a normal subgroup of G. So the proof of this theorem is pretty short. Let A be any element of G. Well, the conjugate of H by A is also a subgroup of G. And the order of this conjugate, A, H, A inverse, is the same as the order of H. Just by coset considerations, every coset has the same size. So the conjugate A, H, A inverse is a subgroup, and it has the same size as the subgroup H. Therefore, these two subgroups must be equal. But again, this is one of our equivalent definitions of H being a normal subgroup of G. So we haven't yet described why normal subgroups are considered to be of particular interest. Well, it turns out that when you have a normal subgroup, we can actually create a new group from the group that we started with. And these are called factor groups or quotient groups. So it turns out if H is a normal subgroup of G, then the left or right cosets of H and G actually forms a group. So we have a notation for the factor group. Let's define that. For a group G and a non-empty subset H, of G, we're going to let G slash H, which kind of looks like a fraction, it's intended to look like a fraction, G over H, let G over H be the set of all left cosets of H and G. G over H is a set of all left cosets AH such that H is in G. So everything in this lesson is kind of leading up to this point right here for this big theorem. If G is a group and H is a normal subgroup of G, then the set of left cosets of H and G over H is a group, and the operation is multiplication of left cosets, so AH times BH will equal ABH. The group of left cosets, G over H, is called the quotient group or the factor group of G by H. So we can either call this the quotient group or the factor group of G by H. So we know that if H is a normal subgroup, then every left coset is also a right coset. So we see that the set of all left cosets of H forms a group. Similarly, we could have said that the set of all right cosets of H and G, it forms a group as well. So let's begin our proof by assuming that H is a normal subgroup of G. And first, let's let AH and BH be two left cosets of H and G. Well, since H is a normal subgroup of G, we can write the product AH times BH as A times the coset HB times H. So here's where we use the fact that H is a normal subgroup. We can write HB as BH. So this is A times BH times H. Again, by the associativity, we can write this as ABH times H. But H times H is just equals H. So this equals the left coset AB times H. So we see that the product of AH and BH is a BH, and that is another left coset. So we see that the set of left cosets is closed under multiplication of cosets. So we know that this set of left cosets is closed under multiplication. Secondly, we'll show that this operation is associative. So let AH, BH, CH be three left cosets of H. Then if we begin with the product AH times the quantity BH CH, we can combine BH times CH as BC times H, and then we can multiply these two left cosets and get A BC times H. Now, by the associativity of the group operation in G, we can write this as AB times C times H, which we can break up as AB times H times CH. And then I can rewrite AB times H as the quantity AH times BH, and then that quantity times CH. So we see that this product is associative. So left cosets are closed under multiplication. The operation is associative. Thirdly, we'll show that 1H is the identity in this set of left cosets. So 1H or H is the identity in G over H. Since AH times 1H equals A times 1H, which just equals AH. And similarly, 1H times AH equals 1A times H, which equals AH. So we see this set of left cosets has an identity. And lastly, we're going to show that every element of G over H has an inverse. Now let AH be a left coset of H. Since G is a group, A inverse is an element of G, and hence A inverse H is a left coset of H. And we claim that A inverse H is the inverse of AH. So let's see that. So AH times A inverse H, that equals A inverse H, which equals 1H. And similarly, A inverse H times AH equals A inverse AH, which again equals the identity 1H. So G over H is closed under inverses. So now any set having the four properties that we just showed, a non-empty set that's closed under the operation, the operation is associative, we have an identity, and it's closed under inverses, we call that set a group. So thus, G over H is a group. So this theorem shows that we can form a smaller group, G over H, from a given group G, and this smaller group can be used to study the structure of the group G, just like we use subgroups to also study the structure of groups G. Now let's give an example of a quotient group. So let 3z be the set of multiples of 3 that are integers. So this will be the set 0, plus or minus 3, plus or minus 6, and so on. So this is the set of integral multiples of 3. And I'm going to construct the factor group z over 3z. So to construct the integers over 3z, we must determine the left cosets of 3z. So again, the set of integers is a group under addition, so we write the cosets additively. Hence the operation on the integers is addition. So then consider the following three left cosets of 3z. 0 plus 3z, which is just 3z, would be the set of all multiples of 3. So negative 6, negative 3, 0, 3, 6, and so on. And then the left coset 1 plus 3z would be all the integers that are 1 more than a multiple of 3. If I add 1 to every element of the previous set, I get -5, -2, 1, 4, 7, and so on. If I add 2 to every element in 3z, we get the set of integers that are 2 more than a multiple of 3. So that would be like -4, -1, 2, 5, 8, and so on. And we see if you add any other integer to the set 3z, you're going to end up with one of these 3 cosets. So these are the only left cosets of 3z in the integers. And we know that the integers is an abelian group, so 3z is a normal subgroup of z. So this set, the set containing these 3 cosets, will be a group. So to see that these are the only 3 cosets, if you take any integer n, then by the division algorithm, n can be written as 3 times the quotient q plus r, where q and r are integers, and the remainder r must be greater than or equal to 0 and strictly less than 3. So if we add n to 3z, that's the same as adding r plus 3q to 3z, but since 3q is a multiple of 3, it's absorbed by the subgroup 3z, so this equals r plus 3z, and we see that this equals one of the 3 cosets we've already listed. So thus, the integers over 3z, the set of all left cosets, is a group. And we can write this as 0 plus 3z, 1 plus 3z, and 2 plus 3z. So this matches up with our original notation for the set of integers mod 3. When we said that every element of the integers mod 3 is actually an equivalence class of the equivalence relation congruent to mod 3. Since 3z is a normal subgroup of z, again because these are abelian groups, we see that z over 3z is a group. So we see that we have the same set as our original definition of the set of integers mod 3. So we actually recover our original definition of the group of integers mod 3 which we defined as the set containing residue classes 0, 1, and 2, where each residue class, like the residue class of A, would be the set of integers that are A mod 3. To see an example of how we do addition in this new group Z mod 3, for example, if we wanted to add two elements of this group, so 2 plus 3z plus 1 plus 3z, then you'd add 2 plus 1, and this would give you 3 plus 3z. Then you would reduce mod 3 to equal the element 0 plus 3z. So this is an example of how you would add two elements of the group z over 3z.